Okay, next one is a chemistry example. This is nuclear chemistry. I'm going to cover the half-life. For the nuclear chemistry, it's kind of a little bit unique in chemistry because it's unique because in chemistry, I would say 95% of the chemistry is pretty much all about the electrons and the electronic property. What we normally consider as a chemistry and chemical property all come from basically large chunk of it come from the electrons. Yes. So if you have atoms, this atom, the nucleus is sitting inside tiny, and largely vacuum, and but the electrons are hanging around somewhere. Yeah? Bunch of electrons hanging out there. But so if it is an example of hydrogen is one nucleus, which is a proton, and the one electron hanging out there. If it's helium, there is a two proton, and there may be two, three, four neutron, and then the two electron hanging out there, and the two nuclei here. So why am I saying this? Because it's mostly it's about the electrons, with the free electrons, which you've learned already by the time you see the half-life. So the main part is what I'm trying to say is typically it's all electronic property, what it is, that's what it is, and all the mole relationship, and what's the metallicity, how metal shines, and all those boiling point, it all come from the basically electrical property. Now, nuclear chemistry, on the other hand, is a bit different because it literally talk about nuclei, and when the nuclei going through the radiation, radioactivity comes, and the half-life. And for that kind of thing, you have to deal with the half-life. Typically, notation is something like this, either this or tau. So let's conceptually deal with the half-life. What is it all about? So, for instance, initially we have to help you visualize better. Let's say this is 100 gram or whatever that is, 100, and it become 100, become to 50, which is half of it, right? To become half, how long it takes, that is what half-life is. Another half of that will be 25 in this particular example. Another tau goes by that. Another tau later, half-life later, it will become 12.5, etc., right? And if you look at this and if you try to formulate what it is, let's see how it's going. Initially, this one, if this is a half-life, this is 100 gram, 50 gram, 25 gram, 125. So if you look at the dot together, it will be basically exponentially decreasing. Yeah. So that's what it is. And initially this was a original mass. Yeah. And we are going to be mass as a function of time, whatever the time is. So originally this when the t equals 0, this is t equals 0, originally is that. That's what it is. And then when the half-life is going through, depends. So when the t was one half-life going through this, is a half of original one. So if it, when is one half-life later, it will be mass is half of the virtue. And if it's two half-life later, it will be quarter of what's the original virtue. So to formulate this, we probably want to write something like this. It is half-life. So for instance, using this data, if t is become tau over tau is 1. So half power to the power of 1 is half, right? So after 1 tau later, it will be half of the original value. Yes. After 2 tau later, if the t is and the t is 2 tau over tau is 2. So half multiplied by 2 will be basically that, right? This one is half divided by 2. So in this sense, this half-life formulation makes perfect sense. Yes. So based on this, let's look at one example. So we had earlier established half as a function of time, and once you establish that, the rest of them is easy because this is a constant. This is constant. Tau is a unique value for the particular nuclear. Different metal has a different, the radioactive material has different tau. So the only thing basically boils down to relationship between M and T relationship, nothing else. Yeah. So if you know how much time it passed, you know how much mass is going to be left out. So example of that category, let's say whatever T may be, and say T was 4, yes, and then original M naught is constant, you should know, have, and T is 4, become 4 tau is a 4 tau over tau, tau cancel off. That's basically the answer is going to be. So in this case, M naught f to the power of 4 is making f to the power of 4 is 1 over 2, 2, 2, 2, so 16. So 1/16th of original M naught is going to be the answer. Yeah, and let's look at another example quickly. So we are trying to find the other way around. The first one is if you know how much time it passed, what's going to be mass will be. If you know the mass, we try to find this one. So let's say mass was new mass. Currently, the new mass is let's say 1/8 of the original mass. Yes, and then we try to find how long it took. Simple, because M is here, M naught here. So in other words, M naught is here. So have T over tau version should be this guy. Yeah. So in that case, when the T is 3 tau, it will become 8. Yeah, because this one times 3 is 1 over 8. So therefore, T will be 3 tau in this case. Okay. I hope that helps. Thank you.